Hi, in this lecture video, I'll be discussing the reaction of alcohol with emphasis on the oxidation reaction of it. And some of the learning objectives of this video are as follows. First, recognize the oxidation reaction of alcohol. Not all types of alcohol can be oxidized, but only some can be oxidized. So what are the alcohol that can be oxidized? We'll learn how to recognize that. And second, we'll be getting familiarized with the different oxidizing agents, their reactivity and their selectivity. And third, the application of oxidizing agent in reaction and synthesis. Now, briefly speaking, we have seen this before already, that alcohol have a various chemical reactivity to them. They are weak base, weak nucleophile, which we have seen them in substitution reaction already. And again, today we'll be emphasizing on the reducing agent ability of alcohol. So alcohol are basically weak reducing agent. And we call them reducing reagent because in this process, they are getting oxidized. So therefore, they are the reducing agent. And they're weak reducing agent. And because they're weak reducing agent, in order for them to react, we need to treat them with a very strong oxidizing agent in order for them to undergo these types of reaction. So first, let's now introduce the term oxidation of alcohol. We have seen that oxidation and reduction are the two opposite processes of each other. If we were to start with an alcohol, we'll be able to take an alcohol and oxidize that into a carbonyl derivative. Whether it is a ketone, an aldehyde, or a carboxylic acid, then those are examples of the carbonyl derivative. And similarly, and in the opposite pathway, if we were to have a carbonyl derivative, we can do reduction of it to convert that into the alcohol. So again, these two processes right here are the opposite of each other. Now, not all types of alcohol can be oxidized, but only some can be oxidized. What are the alcohols that can be oxidized and how do we recognize them? Here's what happened right here. Primary, secondary alcohol can be oxidized, but not the tertiary alcohol. And how we would be able to recognize this is as follows. In order for an alcohol to be oxidized, it needs to have an alpha hydrogen on it. So this is alpha hydrogen. If an alcohol does not have a hydrogen on it, that means it will not undergo oxidation reaction. So no alpha hydrogen, no oxidation. And in the case of a primary alcohol, there are two alpha hydrogen. So a primary alcohol can be oxidized twice. So for an example, here is a structure of a primary alcohol. It can be oxidized twice. In the first oxidation, then this alcohol right here will then be converted into an aldehyde. And notice how that we are removing a hydrogen from this organic molecule. And that is fitting of the definition oxidation. And in that process, this oxygen right here is converted from a single bond into a double bond to this carbon, converting this into a carbonyl. And now that we have this aldehyde already, then this aldehyde right here can be further oxidized one more time into the carboxylic acid. So the number of alpha hydrogen that the alcohol has equal to the number of oxidation steps that we can do with it. So in case of primary alcohol, it can be oxidized twice into the corresponding carboxylic acid. If we were to have a secondary alcohol has only one alpha hydrogen, so it can be oxidized only once. And when this hydrogen right here is been removed and we form a double bond between this carbon and this oxygen, this is now becoming a ketone. So please recognize that in the oxidation reaction, the alpha carbon get one of its hydrogen being removed, and now we are forming a double bond between the carbon and the oxygen to become whatever corresponding carbonyl derivative that it may be. Versus if we were to have a tertiary alcohol, in this case there is no alpha hydrogen, so it cannot be oxidized in the traditional sense. So that's how we can recognize whether an alcohol would undergo oxidation reaction or not. And you can see that the importance of the alpha hydrogen, no oxidation. So what is the role of this alpha hydrogen right here? And then the answer, when we look at the reaction mechanism, we will be able to see why. So it's important for us to discuss the reaction mechanism so we recognize the importance of that primary alcohol right there. And now, let's try this problem right here to see whether you can recognize if something can be oxidized or not. So first, if we were to have this molecule right here with various functional group in them, they have aldehyde and alcohol in them, and different types of alcohol. So if this molecule right here were to be treated with a strong oxidizing agent, meaning it will react completely, then what are we be able to convert this molecule into? Then first one, we will then see that the carboxylic acid is in highest oxidizing state already. It cannot be oxidized any further. And here we have a prime alcohol. So this would then be oxidized into the corresponding carboxylic acid. And this alcohol right here, this is a tertiary alcohol, right? So this cannot be oxidized. This is a secondary alcohol, so it can be oxidized into the ketone, and the aldehyde can be oxidized as well into the carboxylic acid. So in the end, the product of this molecule would then be as follows. So the carboxylic acid, nothing happened to it. As for this primary alcohol down here, it be oxidized into the carboxylic acid. And now this tertiary alcohol will remain intact, nothing happened to it. And this second alcohol will be oxidized into the ketone. And now this aldehyde will then be oxidized into the carboxylic acid. So if this molecule right here were to be treated with a very strong oxidizing agent, that is what it will be converted into. And now we'll be going over some of the common oxidizing agents. There are various oxidizing agents that are out there, providing different types of reactivity and selectivity toward the different functional group. So it's important that we begin to gather all of this information and basically make the list of the different oxidizing agents and understand how they work, and think of them as tools and add them to our toolbox. So that way we can pull them out, this reagent, whenever applicable to do any reaction that we need, whether we need to be selective or not selective. Now, so again, different types of oxidizing agents have different reactive activity to them. Some of them have preference for one particular carbonyl derivative functional group over the other. And some of them are pretty weak. If we were to have a weak oxidizing agent, then it will react more selectively. So again, this is the trend between reactivity and selectivity. The more reactive a reagent would be, then that one will not be providing selectivity. Versus the less reactive would be, it will react with some but not the other. So that when we get the selectivity. So we'll be getting started with the first oxidizing agent, and this is basically called the chromic acid, or derivatives or oxidizing agent involving the chromic acid. So, and this is commonly known as the Jones oxidizing agent. So the Jones oxidizing agent basically involves the use of the chromic acid to prepare that reagent right there. So Jones reagent. In this Jones reagent, or this chromic acid oxidizing agent right here, it involves a chromium with the oxidation state of +6. So that's a very high charge of the oxidation state right there. And therefore, it is a very powerful oxidizing metal. And so basically, because this is +6, therefore, it would like to accept electron, right? And because it like to accept electron, therefore, it is the oxidizing agent. And the reason why I like to accept electron is because its charge or its oxidation state right now is already +6. Something with that high of a charge right there will be happy to accept the electron. Therefore, making this chromic acid right here, in which the charge of the chromium is +6, it can accept electron very, very well. And so there are several ways how we can prepare this chromic acid. We can start out with chromium trioxide, reacting this with acetone and water to convert this into the chromic acid. Or we can also start with the sodium dichromate and mix that with acid and water, and that will also produce this chromic acid as well. And so basically, these are two different ways how to prepare this chromic acid. And this method right here is then known as the Jones reagent. So this one is known as the Jones reagent. Now, so the chromic acid will oxidize primary alcohol, secondary alcohol, and aldehyde as well. because if anything can be oxidized, it will get oxidized. We cannot oxidize a ketone, so therefore ketone will not get oxidized, but the aldehyde can be oxidized because on the carbonyl carbon on the aldehyde there is a hydrogen in it, and that is the hydrogen that can be oxidized. And primary alcohol is then oxidized by the chromic acid into the corresponding carboxylic acid, and same thing with the aldehyde. So if we were to start with a primary alcohol and we treat this with the chromic acid reagent in the presence of water and acetone, first we'll be able to oxidize this into an aldehyde. But it's really difficult to isolate this aldehyde right here because this aldehyde is still reactive. So therefore, even if we're not adding a lot of reagent in excess, the reagent will be able to come in and oxidize this aldehyde right here into the corresponding carboxylic acid. So it's not possible to stop at the aldehyde if we were to be using Jones reagent or the chromic acid. And if we were to have a second alcohol, and we again treat this with the sodium dichromate, this is another way how to produce the chromic acid. Then we'll be able to oxidize this into the ketone. So again, please recognize that this have one hydrogen, so it can be oxidized once, producing the double bond. So this hydrogen has been removed, and now we are creating a double bond between the carbon and the oxygen. Therefore, we get in this ketone right here. And now we're going to go over the mechanism of an oxidizing agent, and hopefully you'll be able to understand the importance of having that alpha hydrogen. So here is structure of a second alcohol right here. And when we take this and react in this with the chromate, then what happens is again, this chromium right here is highly electrophilic because it has a lot of electrons, electronegative atom pulling electron from it. So therefore, the alcohol will then come in and attack that chromium right there and kick up one of this bond right here and converting this into something that we call the chromate ester. Of course, followed by the proton transfer, which we would skip because we want to focus on the key step in this reaction right here. So initially, the alcohol will react with the chromic acid to convert this into the chromate ester. Once this chromate ester right here has been formed already, it is very important that we recognize this following step right here. So water would act as a base undergoing an E2 reaction where we come in and pick up this alpha hydrogen right here. And now, once this alpha hydrogen right here has been removed as a proton, the electron is then donated into this oxygen, to this oxygen and carbon forming a double bond right here. And this oxygen right here is then given the electron to the chromium plus 6. And that is a very key step right there that explains the formation of this double bond. And now, so the reason why this can also make sense as follows. Initially, we see that the charge on this chromium right here is positive 6. So it really wants the electron. So therefore, we can think of this in the opposite way, where this chromium is taking the electron away from this oxygen. Once this oxygen right here, it lost the electron to the chromium, it now will not have an octet of electron. And therefore, it can accept an external electron. So therefore, it can pick up the electron from this, the bond between this carbon and this hydrogen. If this hydrogen right here were to be removed, so this is why that water acting as a base, come in, pick up this alpha hydrogen. And the electron between the carbon and hydrogen can then be donated in to form a double bond between the carbon and the oxygen. And now the oxygen will be happy to give the electron to chromium. So in the course of this reaction mechanism right here, the chromium is gaining the electron. So that's why that now it will be changing into the plus 5 on the resultant product. So the oxidation state of the chromium is changing and it is accepting the electron. And that's the reaction mechanism. So it's important that we have this alpha hydrogen right here. If there's no alpha hydrogen on this carbon right here, then on this alcohol right here, then it cannot be oxidized. And this is the explanation why the tertiary alcohol cannot be oxidized. And now let's now go over another oxidizing agent. And this is called the pyridinium chlorochromate, abbreviated with PCC. This oxidizing reagent right here is slightly more reactive than the Jones reagent, in which that is now suitable for the synthesis of aldehyde. If our goal is to stop at the aldehyde and cannot or not oxidizing the aldehyde, then we need to use this PCC right here. Because once it will only oxidize the alcohol, but will not oxidize the aldehyde. So it is more sensitive and more selective. And the PCC, it basically also involves the use of the chromic acid as well, except it have the pyridine in it. So basically, essentially, it is the same thing, except that it is the less reactive version of the chromic acid. And it, so here in example of it right here, if we were to have a primary alcohol and treating this with PCC in the presence of dichloromethane, we'll be able to oxidize this into the aldehyde. And similarly, if we were to have our second alcohol and we treat this with PCC, we'll be able to oxidize this into the corresponding ketone. Now, please note the following. There's no water in this PCC reagent right here. So we simply take pyridine combined with this chromium trioxide and HCl and producing this PCC reagent right here. And now let's try some of this example right here involving recognition of this different oxidizing agent. So first, number 39, if we were to take this molecule right here consistent of an aldehyde and the primary alcohol, and we treat this with the chromic acid, so this is the Jones reagent right here, what will be the product? So first we see that this is a very strong and powerful oxidizing agent. It'll be able to oxidize both the primary alcohol and the aldehyde. So therefore the product would then be the following. So the aldehyde will be oxidized into the carboxylic acid. Please note that it does not do anything with the stereochemistry of this carbon right here. And same thing with the other carbon. And as for the other carbon, this would now be oxidized into the carboxylic acid as well. So both primary alcohol and aldehyde will be oxidized into the carboxylic acid. But if we were to now take this and react this with PCC instead, then PCC will not react with aldehyde, but will only react with a primary alcohol to convert that into another aldehyde functional group. So the product of this reaction would then be following. Again, this aldehyde remains intact, and as for the primary alcohol, it will be oxidized into the aldehyde. So that will be the product of this reaction.